So good morning. Late morning. Any questions about the reading? Let me remind you that Lab 1 starts Thursday night and Thursday 4 p.m. We'll hand out, we'll show you where the boards are, give you access to the cabinets, all that kind of stuff. Then, a couple of people have picked up SD cards already, and you can do that at my office, assuming you're not going to drop the course. 40 people are still signed up. There's not 40 people here, so I'm assuming that this subset is serious. Again, any questions about the reading? What I want to do today is talk a little bit more about the general tool flow, then talk a little bit more about Lab 1 code specifically, and then talk about Verilog, background of Verilog, a little bit of background of Verilog, preparatory to looking at the code for a Avalon Busmaster, which is what the rest of the course is going to be about. So, I thought I'd try and give some idea of how all of these, the Qsys and Qsys Prime and everything hooks together here, unless that's obvious. But Qsys 2 has been renamed Qsys Prime, and that was before Intel took it over. And what you're going to put into Qsys Prime is your Verilog, and possibly, as the semester goes on, memory image files. Memory image files are in a format that Qsys Prime can convert into ROMs on the FPGA directly. And it's a very simple text formatted file. But this allows you to preload, say, code onto the FPGA if you're building a processor, or a ROM table if you're, say, building a direct digital synthesis unit. Signal tap also feeds into Qsys Prime. You set up signal tap, it interacts actually rather closely with Qsys Prime, because signal tap will know, when you invoke it, will know about the signal names in your Verilog file and allow you to expose those by recording those signals into RAM blocks and then spitting them out through the USB blaster connection back to the PC so that you can view them on a simulated logic analyzer. So this is real-time, real data, not simulation, that comes out of Qsys Prime, out of the FPGA. So the FPGA is going to sit down here and get a design from Qsys Prime by the so-called USB blaster interface, which has all kinds of capabilities for serial communication and all kinds of stuff. Hooked to the FPGA is at least 2 big blocks of DRAM, and you're going to put C code directly onto the FPGA via serial line or by Ethernet directly to the HPS core. Feeding in the top of this is Qsys, which used to be an integrated tool in Qsys Prime, but now has been broken out separately. And this allows you to do bus layout. So you're going to be inputting a bus layout in a graphical language. I don't care for graphical languages. I don't think they're terse enough. They don't scale well once you get past a screen full. But it's a graphical language. Bus layout. And in particular, you're going to have input here which you're going to have to use, which is the university. No, that's wrong. University IP collection, which you can get to on any machine that has Qsys 15 installed. You're going to want to go to, on the C drive, Altera feels like they need their own directory. So it's Altera / 15.x, 15.1, whatever it is. University program. And from there you can follow down and find the IP that's available. And what's going to feed in here is a gigantic piece of Verilog, which is the bus description. And you are going to then be able to cut and paste the top level module that describes the bus structure .v file into your Verilog into Qsys. So that's the sort of overall tool flow. Any questions on that? So this is a graphic layout language. This is Verilog is going to be there's an editor built into Qsys Prime that some of you will like and some of you will hate, but you can edit however you like. You're going to compile this. The compile step is slow. Oh, there's also model sim. You can take your Verilog. You can take your Verilog, put it over into model sim, write a test bench for it, and simulate it. You're going to find that's very useful for compute modules, like for instance in Lab 2, when you have to build a simulated analog computer on the FPGA fabric. You're probably going to want to simulate it before you connect it to a bus master, where you have to then compile it through Qsys and Qsys Prime, and 15 minutes later you can find out it doesn't work. So I wrote a single-page description of how to use Model Sim. There's also a tutorial online from Altera on how to use Model Sim. There's a rather long tutorial on Signal Tap. But ultimately, when you're building real-time systems, the only way to test them is to build them. Because there's no way you're going to simulate the VGA monitor, for instance, to see if the system is working. Any questions? Let me go back and pick up a couple of details about Lab 1. As I said last time, Lab 1 is going to take a piece of code I wrote, the Conway's Game of Life on HPS. I'm going to ask you to take the C code and add mouse control to it. So I thought I'd say a couple of words about that. And also, I want to say a couple more words about mapping addresses onto mmap. So, as I said, the the computational piece of this lab is essentially written. You may want to tune it a little bit. And you're going to want to use the better chopped down system, which is at the top of the screen there. That project zip, the code, a header, and so on is what you want. There are 3 peripherals that this code uses. There are 3 peripherals that this code uses that you're going to need to interact with on the FPGA side. One is the H2P lightweight bus. The lightweight bus, and we'll have to get an address for that. Anybody remember already what the address is? FF200000. You'll know it by the end of the semester. And then there's a pixel virtual base, which is really a pointer to the beginning of on-chip memory. And then there's a character buffer, which is independent of the pixel buffer. In other words, the characters are overlaid on the graphics and are not part of the graphics. So you can modify the character plane without modifying the graphics, and vice versa. So that has its own memory description. One of the limitations of the implementation of the character buffer is that I find annoying is there's only one size character, and it's always printed in white on a transparent background, which means you can easily make unreadable text. Maybe somebody for a final project would like to make that full color. So then, as we did last time, I talked about how to do the mapping from using mmap to get from physical addresses to virtual addresses that we can actually touch in the program. Are there any questions on that? So what we're going to find is that if we want to get to a certain pixel on the VGA, there's going to be this pixel base, wherever I put it here. VGA pixel pointer. So what we're going to find is that VGA pixel pointer actually points to that pixel, upper left corner, 0, 0. And that to get to any other pixel on the screen, we're going to add an offset. And the offset is going to be of the form with y running from 0 to 479 and 0 to 639 is going to be equal to y shifted by 10 bits plus x bytes. Why y shifted by 10 bits?
Because that's the column?
Yeah, it takes 10 bits to represent one width of the screen. We're not using all of the 10 bits, but it's more than 9 bits. So when you write to a pixel, it's equivalent to modifying the value stored at this memory location. Likewise, there's going to be a character pointer and an offset into character space, which will give you the character number, but the character map is 0 through 79 and 0 through 39? I made this mistake once before. I think it's 39. Maybe it's, yeah, I think it's 39. I think it's 80 by 40 rows. The last thing we're going to do is to, as I mentioned, is to write to the, or we're going to need to have access to the H2P lightweight virtual bus. So we have H2P lightweight bus. And to get to the switches, which you're going to need for lab 1, you have to add the switch offset to that bus base. The switch offset is defined in Qsys. Let's see if I can completely confuse myself by forgetting where I am on which page. Already forgot. Oh, I know what yes. The Qsys that describes the university computer scaled to the screen is about as tall as I am. And so it's very difficult to show on an overhead. But the hexadecimal offset that you will get when you go and look at that Qsys file, like today, will be 0x040. So 40 bytes above the bottom of the bus definition are the switches, and that's obviously read-only. Because if you write to it, it's not going to flip the switches for you. Only, well, wouldn't it be nice if it could? So, 3 separate bus entities you're going to have to deal with. 2 are slightly hidden from you because my VGA write routines package this up slightly. If we go down towards the bottom of the oh, for instance, text clear. Oh, there's a mistake in here. Yes. I'll let you figure it out. So VGA box does a bunch of range checks, and I think I showed that last time. But in the end, all it does is to write 1 byte to the character pointed to by pixel plus row shifted by 10 plus column. So that's slightly hidden from you. And this version of life ran somewhat faster because I only wrote when I had to. It turns out that the bus transactions, writing VGA pixel, is a bus transaction that goes off through the FPGA interface structure, is so slow that you want to avoid those unless you absolutely have to actually write a pixel. So it was quicker to make sure I needed to write a pixel than to just write it. And that sped up the code a factor of 2, 3. The other thing that sped it up over the first pass, and as you all know, once you write a program, you can always speed it up a factor of 3 to 10. I got rid of this homely C-based copy operation and replaced it with a mem copy. So this is probably the version you're going to want to use. Was there any questions about this code? It's very generic C code, except for this mmap stuff at the beginning that sets up the I/O addresses. So the other piece of this that you need then to work is the USB stuff, and this is really simple. All you're going to do to read the mouse is to open the mice interface. There's only one in this case. Open the device, apply a file definition to it, and then read in a loop. In your case, it'll be probably once per frame. If bytes is greater than 0, if bytes is 0, it means that there was no mouse event and you should skip it. Otherwise, you can read the left, right, and middle buttons from data 0 and the X and Y from data 1 and 2. This is not actually the position, this is the delta position. So it's delta X and delta Y. So typical motion values for X and Y will be +1, -1. Sometimes +2, and if you really whip that mouse, +3. So you have to do then a numerical integration to get the actual position on the screen. In other words, you have to sum up the delta X's and delta Y's, and then use that as a way to position the mouse. So when you start the program, when you start a real program, what you're probably going to do is put the cursor in the middle of the screen. You're going to initialize the integrator to the cursor coordinates where you set the crosshairs. Maybe that should be an X in the character map. Anyways, where you set the crosshairs, and then after that you're going to integrate deltas away from that initial position that you set up on the screen. Any questions on this? I think it's pretty straightforward lab, except that every single thing will be new to all of us. And that's what makes it not straightforward. But that's why we're giving you 3 weeks. The prudent among you will try and finish as fast as possible and start lab 2, which is much harder. Because unlike lab 1, the rest of the semester will be the bulk of it will be Verilog. Questions on lab 1? It's very quiet. Yes?
Could you go back over how exactly you get the addresses from memory mapping?
Oh, sure, yeah. So there's...
How exactly you should
So let me give you, the long example is too long to put on the screen, but let me give you a small taste of the Qsys layout here. Let's see, which one is good? So let's look at this one. So we have can you read that from the back of the room? How's your resolution? As approximate 20-year-olds, the best resolution you can have is a fairly large fraction of 1 milliradian, say half a milliradian or so. 1 or 2 of you will be down at 1/10 of a milliradian. And people like me are up about 100th of a radian. But the first block of this is the ARM, then the LEDs, and then some hexadecimal stuff, and then an external master. So let's zoom in on hex 0 through hex 3. Hex 0 through hex 3 are the 7-segment displays that you have available on the board. And if we go over here to the right, we see that that is at offset 20 on the bus. And in fact, has a range of 16 bytes. So that is where the bus offset comes from. It comes from the right-hand column of the Qsys layout. And you're going to be looking for, well, the LEDs are at 0. Oh, I left the slider switches in this one. There it is. 040. Hexadecimal 40 is the offset. So to get the absolute address then, you have to add the bus base address to this offset. Where do you get the bus base address? In my thoughtfully provided address file. So we go to this address file and we find that the hardware registers base is FF2 00000. So there's a predefined symbol for that, and I think there's a switch base in here. Switch base 40. So as long as you don't mess with the Qsys layout, if you start hacking addresses on Qsys, you get to redo this file. Because they have to agree, right? The Qsys bus assigned addresses in Qsys, that's where you get to type them in, have to match this file, which is what C is going to generate to get to those addresses that you defined in Qsys. Does that answer?
Yeah.
So in your C code, you're going to do a write to the pointer, the value of the pointer, which is the hardware register base plus switch base.
And what's the point of memory mapping it?
So you can get to it at all.
Okay.
So think of this as it's an output register from the point of view of the HPS. It's an output register. From the FPGA side, it's a chunk of hardware that you've mapped onto the bus. Anything else? We'll do this a couple of more times because there's lots of moving parts in this. So I want to talk about bus masters, but I thought I ought to do a little bit of Verilog review because about half people held up their hands when asked a couple of critical questions. So I just want to talk a little bit about Verilog. And probably some of you have used Verilog for simulation, and some have used it for synthesis. How many have used it only for simulation? How many have used it only for synthesis? 2 of you? How many have never done a damn thing with it? Okay. A couple honest people. So we're going to have synthesis. We're going to do synthesis only. And Verilog was originally written as a simulation language as well. And the simulator does all kinds of things because it's running in a computer environment. But when you're building synthesizable code, you cannot assume that you have a computer that's hosting that code. It's just the hardware. So, for instance, there is no init statement. You cannot init a register in the code and expect it to be initialized, you have to explicitly write a state machine with a reset state. And in the reset state, you reset the registers. Now, there's one slight caveat on that, and that is that if you put an init statement in Verilog for Qsys prime, it will say, at the time I burn the design onto the FPGA, I will set that register. But then if you press reset, you don't get that value back again. So, no init statement. No system calls. So, there's no print capability because there's no printer. It's just whatever hardware you build. There's no ability to get a value out of memory because there's no memory unless you define it. There's no floats, no reals, no floats. In fact, I would call this a very untyped language. You have one type, a register. It holds bits. You can do anything you want with those bits. You can call them a float if you write a floating adder. You can call them a fixed point number if you write a fixed point multiplier. You can call them anything you like, but it's just a pile of bits. There's no timing information in the program. There's no delay keyword. There's no timing info because timing is determined completely by the hardware clock. Nothing's sitting there saying, I've got to wait 30 nanoseconds. If you want to wait 30 nanoseconds, you take it off in a clock someplace, in a hardware clock. Loops. Loops are not sequential structures. They are not sequential. They rather represent copied hardware. So if you loop through something 100 times, you will build 100 copies of that hardware. But it will not be sequentially executed. It will be executed all at once. So effectively, don't use loops when you're building hardware. A module sort of feels like, looks like a function. It looks like a C function, but it's not. When you instantiate a module, you're making a copy of the hardware at that location, at that connection location. So if you instantiate a module in a loop 100 times, you're making 100 copies of that module and putting them all on the FPGA. So a module is not a function. It is a piece of reusable hardware. Every assign and always happens all the time. If it can happen, it does happen. There is no sequentiality to a program. An always block that is combinatorial, you can think of as happening instantaneously. Although, of course, there is a propagation time through the actual physical hardware. The only way to get a clock rate is to write an always block that is locked to a pos edge or a neg edge of a clock. So the language is completely simultaneous and parallel.
Is negedge synthesizable on these chips?
Say again, negedge?
Is negedge synthesizable on these chips?
It is synthesizable, but you can't use both. You can't say on, always on pos edge or neg edge. You can say neg edge or pos edge, but not both. There's no tri-states. No tri-states on cyclone 5. Cyclone 5, except I/O pins. That's because internally you can always build a multiplexer. So you have no tri-states. That means you will very, very rarely use the symbol Z. 0, 0, Z, 1, 1 is a vector whose middle bit is tri-stated. You won't do that unless you happen to be writing an I/O driver for a memory chip with a bidirectional bus or something equivalent. So the tri-state, the high Z, the high impedance keyword you'll never use. You may find a use for the X keyword, the X symbol, which means don't care. So 00X11 means I don't care what that bit is. It's defined. It has a value. It's either 1 or 0, but I don't care. And then virtually the only time you'd ever use this is in a compare. And even then, do it carefully. An incomplete case or if else can infer a latch. And I'll go through that in more detail. But since a wire always has to have a value, if you have a conditional that doesn't give the wire a value, the compiler says the only reasonable thing to do is to give it the last value that you specified. And so you get an inferred latch, you get a clockless flip-flop put into your design, which can just mangle your timing, make the system not operate. I'll talk more about that. I want to write some code out in detail on that. So this is a very constrained language. It is almost typeless. It is weakly typed. It is basically manipulating strings of bits at a very low level, although you can build up an abstraction if you work at it. And all sequentiality, all sequential behavior is explicitly handled by state machines that you write. There is no implied sequentiality in the program structure. Any questions? Let's talk about inferred latches just a little bit. Let's say that you write a little snippet of code that looks something like always at, and I could write out a sensitivity list, but a sensitivity list on an always statement really reflects back to the simulation where you have to worry, for the simulator to be efficient, it has to know what changed. Everything always changes in hardware. So you may as well just say at star, which means do the right thing. So let's say we have a case of some 2-bit variable called select. So this is two bits. And so for the case of 2B11, 2 bits of binary 11, we're going to set a 1-bit value D equal to A. And you'll notice I'm using a blocking assign here, but we'll talk about that later also. And 2B 1 0 D equals B, and 2 tick B 0 0 D equals C. End case, and always. Oh, I better put begin here. And always. Comment. I tend to always comment my ends so that I know whether it's an if end or an always end or a module end, because once you get past a page, you can't keep track of it anyway. So the question is then, what happens in the inevitable case where select is 0, 1? None of these are assigned. And so the compiler says, in that case, the silly user wants the last value of D and therefore will infer a latch on the D variable. So you are crazed if you don't put a default into here. So the solution for this is you say default equals D equals A, or whatever you want. You can either make sure that you have every possible bit combination, which you will obsessively check. With 2 bits it's pretty easy. With 10 bits and some don't cares, it becomes harder. Yeah?
Can you set a global default for the variable? Like, let's say you use it a lot, like in different places, you can't have it fall back on something.
I don't believe so. Does anybody know an answer to that? I haven't seen
You
it.
can set it at the beginning of the always block. So you just set D equals A at the beginning of the
Or you can say D equals A before you go into the case.
Yeah.
And because these are blocking statements, it'll do that first and then undo them if necessary. And this is not, and when I say blocking, it doesn't mean, if I said D equals A up here, it does not mean that this is first set to A and then changed at a later time. What it means is a logic tree will be built so that the final outcome is either A or the result of the case statement, but it's instantaneous. Likewise, if you build an if statement with a else if, else if, else if, make sure that at the end of that there's an else. Make sure there's a default else, or make sure that you've covered all of the bases. And this can get hard. If you have a bunch of else ifs all that have weird condition in them, you virtually can't guarantee that you've covered all the conditions unless you have an else in there. This makes errors that are so hard to find. And it's not an error. You might want to do that. And so it's a warning. And so if you're starting to get weird results, there's a couple of things you want to always check for in the warning list. There might be 800 warnings, right, of which 3 matter. So you're going to want to search that for the keyword inferred. So you're going to want to search warnings for the keyword inferred. And I did one the other day, which it's a mistake I know I make. So I was pretty sure I made it when the results didn't work out. And the effect was I was building an audio signal output, and I added one more filter and everything completely broke and the output was completely silent except for a little bit of crackling. And that was because I neglected to declare as a multi-bit register the output as a multi-bit wire, the output wire from the module. Neglecting to declare is not an error. It is a warning, because if you just use a variable, it defaults to a 1-bit wire. And so you want to always search for the keyword implicit, because that'll pick up variables that you or signals that you forgot to declare. If what you wanted was a 1-bit wire, it may work anyway. But if it's a multi-bit wire, it won't. So those are always worth searching for in the warnings. Anybody else have any keywords they like to look for? Those are the two that'll kill you. I want to talk next time a little bit about blocking versus non-blocking assigns. Again, any questions here? Yes?
Does this work with system Verilog as well?
Couldn't tell you. Never used it. Anybody know? System Verilog, I believe, is a generalization of Verilog. So I think everything I've said is probably still true in System Verilog. There's a few more things you can do, like pass two-dimensional arrays of vectors into modules, and a few other things like that that you can't do in Verilog, but I don't know any details about it. It takes a lot of hours of programming before I feel comfortable saying anything about a language. What else? So the plan now is to talk a little bit more about Verilog and then go back and pick up some material on bus masters. And what I'm going to do is to use the VGA display bus master example, since that's relevant for Lab 2, and also then talk about the audio output bus master, which is more complete because it does a complete read-write cycle to read a FIFO state, write the FIFO, read another FIFO, and if there's data, read the data. So it's doing a bunch of interlocked operations. So I want to talk about that. That'll also get us right down to the nitty-gritty Verilog level. Anything else? So Wednesday, I will collect all of your names on a sheet of paper to give to Patty for door access to the lab. And Thursday night, we'll set everybody up with hardware. See you Wednesday.